Alright, hello class. In this video we're going to be talking about the Fundamental Theorem of Calculus. So this is actually the section where everything sort of comes together and we get the final answer to those concerns we had when it came to definite integrals. So this is how we can attack definite integrals without needing the limit. Okay, like we did before, or needing geometry to do it for us. And it actually, the fundamental theorem of calculus itself is a theorem that connects integrals and derivatives together. Okay, and it does it in an official manner. Alright, so let's actually just start with talking about what the fundamental theorem of calculus is. There's two parts to it, and we're really just going to focus on one of the parts here. Okay, but there's another one that kind of goes in the reverse. We'll talk about that one too, but for our purposes in this class, the main one we'll be talking about is, I think it's what the book calls part 2, but I consider that the main one, at least for everyone first learning this stuff. All right, so let's just get to it and talk about what the fundamental theorem of calculus is. All right, so here's what the fundamental theorem of calculus says. As I said before, there are two parts to this, and this is what the book calls the second part, but to me it's probably the most important one we'll be using. And just to give you a hint in general, if you're ever in a class and something is called the fundamental theorem of the name of that class, you can pretty much guarantee that it's extremely important, possibly one of the most important theorems in the entire subject. Okay, so anyway, the fundamental theorem of calculus, which I often abbreviate as FTC, says that if f of x is continuous on a to b, and that should be an and capital F of x is any antiderivative of little f of x on a to b, then the definite integral from a to b of little f of x dx is equal to simply capital F of b minus capital F of A. And that's it, okay? That to me is incredible, because if you remember, what we were looking at before for the definite integral was this thing. We had f of x dx. It ended up being the limit, right, is n goes to infinity of delta x times the sum k going from 1 to n of f of x sub k, right? And that limit, right, is what would give us that actual area. But by the fundamental theorem of calculus, it just says, hey, if you want that area, you don't have to take this limit of this nasty sum. All you need to do is find an antiderivative, take it, plug in the top number, plug in the bottom number, and that's it. That's literally it. Okay? And if you think about it in terms of displacement, right? So if you remember when we were talking about physics stuff, the displacement over a time interval a to b is actually the definite integral from a to b of v of t dt is the definite integral of the velocity. And so what this is saying is it will be the antiderivative of the velocity. Well, that's the position, so it will be the position of b minus the position of a, and that is the exact definition of displacement, right? And this is what we get also from the fundamental theorem of calculus, okay? So it's actually kind of amazing how simple this ends up being, especially considering what it is the definite integral is, right? That's that horrible limit where we let the number of rectangles go to infinity while the bases of those rectangles go to 0. That's an extremely complicated idea, an extremely complicated concept, but thanks to the fundamental theorem of calculus, it's literally just a difference. We just need to find an antiderivative, plug and chug, okay? An equivalent way to talk about the fundamental theorem of calculus, we can also talk about it in terms of the derivative. So equivalently, All right, if f prime is continuous on a to b, then the definite integral from a to b of f prime of x dx is going to be the original function, f of b minus f of a. Okay, so that's an equivalent way to talk about the fundamental theorem of calculus in terms of the derivative to the original function versus a function to its antiderivative. Okay, now let's verify this. Let's take a look at that example we did before using the limit in the previous lesson and see if it lines up with what the fundamental theorem of calculus says. Okay, so to verify, let's consider the definite integral 0 to 4 of x squared dx. So previously, we found that this was 128 over 6, or 64 over 3. Don't know why I didn't just jump to that version, but this is what we found previously using the limit definition of the definite integral. Now let's use the fundamental theorem of calculus. Okay, now here is how I think is the best way to notate this. Okay, so we're going to write our definite integral. So we have the definite integral from 0 to 4 of x squared dx. Now, I need an antiderivative of x squared. So the antiderivative of x squared is 1/3 x cubed. Now, we don't really need a plus c, and I'll show you why that is in just a second. So just bear with me real quick. So here's the antiderivative of x squared. It's 1/3 x cubed, and I always put a bar, a big bar here with 0 to 4, because what this tells me is I'm going to plug in the 4 and then plug in the 0 and subtract. Okay? This is just a nice way to be able to do it all in one line instead of like, okay, here's what capital F is, and here's f of, say, b minus f of a. We can just say, okay, here's the antiderivative, and I'm going to evaluate it from 0 to 4. We're going to plug in the 4. All right, so I have 1/3 times 4 cubed. Okay, minus, now we'll plug in the 0. So it'll be 1/3 times 0 cubed. Okay, now 4 cubed is 64. This comes out to just be 0. So we get 1/3 times 64, or 64/3. There we go. That's exactly what we got doing it the long way before. Okay? So hopefully you can see that this is a much quicker process than what we had to do previously. In fact, what we did previously required us to look up some like table values of sums, and those don't exist for every single possibility we might ever find. So the fundamental theorem of calculus is a much more efficient way of doing this, obviously. So this is kind of like the difference between finding the derivative with a limit definition versus finding the derivative just with our rules. Okay? All right, so I think this just brings us to the point where we can just start doing some examples. So let's just look at some examples. All right, so for first example, let's consider the definite integral from 0 to 2 of 3x squared plus 2x dx. All right, so to give an idea of what we're looking for those visual learners like myself. All right, so here's the graph of 3x squared plus 2x. I'm zoomed in a bit because we're really only looking from 0 to 2. And that definite integral from 0 to 2 of this function, 3x squared plus 2x, is this area here, the area between the curve and the x-axis. So that's what the definite integral is going to give us. All right, so let's check it out. Okay, so we're going to start, of course, if we have the definite integral from 0 to 2, we're going to start by taking the antiderivative. All right, so the antiderivative of 3x squared will be 3 times 1/3 x cubed. All right, then plus the integral of 2x, which will be 2 times 1/2 x squared, and will be evaluating this between 0 and 2. So this bar here, okay, so remember this is how we write that fundamental theorem of calculus idea that we're going to be plugging in the 2, plugging in the 0, and taking the difference. But of course, we'll want to simplify this first. So we'll have the 1/3 and the 3 cancel, so we'll have x cubed plus x squared, and we're going to evaluate that between 0 and 2. So we'll plug in the 2, so it'll be 2 cubed plus 2 squared. I always like to put parentheses around the entire thing just in case. We won't always be subtracting by 0. Of course we are in this case, but that's not always going to be how this works. Okay, so we're going to have 2 cubed, which is 8, plus 2 squared, which is 4, minus 0. So the area here is 12. So the area beneath this curve and the x-axis is 12. Now, if you ever wondered, right, if you ever wondered how people found, so if you ever wondered how people found like areas of strange functions, right? If you ever were curious about how that worked, a lot of times it's using integration. Right? If you ever wondered how you could find the area of something wavy, that's how. They're using integration and the fundamental theorem of calculus. All right, let's look at another example. All right, for our next example, let's look at the definite integral from 1 to 4 of x minus 2 all over the square root of x. In order to start, we can't just integrate this as given. We're going to have to simplify it a bit. So we'll keep all of our integral signs. So we don't drop the integral sign or anything like that until we actually start integrating. So we will break this fraction apart to get x over square root of x minus 2 over square root of x dx. And now I'm going to write these as powers, right? So this is x to the 1 over x to the 1/2. So this is going to be x to the 1 minus a half. And this is 2 over x to the 1/2. So this will be 2 times x to the negative 1/2. All right, so now let's clean this up a bit. This is the integral from 1 to 4 of x to the 1/2 minus 2x to the negative 1/2 dx. And now we are ready to integrate. So let's do it. This is going to be x to the, when we add 1, 3/2 times its reciprocal. So it'll be 2/3 times x to the 3/2, then minus 2. The 2 comes along for the ride. And then it will be x. When we take negative 1/2 and add 1, we'll get positive 1/2. We multiply by the reciprocal, which is 2 over 1. And we're going to evaluate this from 1 to 4. Okay, so I have 2/3 x to the 3/2 minus 4x to the 1/2. Well, x to the 1/2, that's square root of x, right? X to the 3/2, now this is something I think many people kind of forget, have problems with. X to the 3/2, that's the same thing as writing the square root of x cubed, right? That is x to the 3/2. Now the reason we might want to do that, or you could also write it as the square root of x all cubed, right? You can do it in either order. I think this is probably the wiser way we would want to. And why that would help is because we know what the square root of 4 is, right? So when we put in 4, square root of 4 is going to be 2, and then we cube it, okay? So, and 1 is a similar idea, okay? So this will be, let's plug in the 4. So this will be 2/3 times the square root of 4 cubed minus 4 times the square root of 4. So we have plugged in the 4, and we're going to plug in the 1. So this will be 2/3 times the square root of 1 cubed minus 4 times the square root of 1. Now here, I will tell you that when, in my labs it probably doesn't matter because they just want that final answer, but for me, if you're doing anything by hand or in class, after you get to this part, right, I'm not really concerned with what comes after, right? That final answer, getting from here to the final answer is literally just arithmetic. Okay, I assume that you all know how to do arithmetic by this point. What to me is important is getting up to here, showing the plugging it in, right? You plug it in the right order. That is what I think is important. Okay, so that final answer, that final number might be worth a point. Okay, it might not. In fact, if you wanted to, say on an in-class quiz or test, if you just wanted to stop here, I don't think I'd be able to count that wrong because that is still correct. Now, of course, we are going to simplify this a bit, but to me, the integration and plugging it in the right order is what is key. It's what's important. Okay, so anyway, this will be 2/3 times 2 cubed minus 4 times 2, and minus, I'll keep the parentheses, this will be 2/3 minus 4. All right, so we'll have 2/3, 2 cubed is 8, minus 8, minus, I'll just distribute that minus sign, minus 2/3 plus 4. Now let me show you a quick way to do certain things here. This is 8 times 2/3, and this is 1 times 2/3, so you could actually, when you subtract, say that that's 2/3 times 7. Then the minus 8 plus 4 is, of course, going to be minus 4. And so we're going to have 14/3 minus 4. And then 4 is going to be, when we put it over 3, 12. So I have 14/3. All right, and so 14/3 minus 12/3 is going to be 2/3. Okay. Now if we look at the graph, here's the graph of our function, x minus 2 over square root of x. And if we look at the area, so remember when the function is below the x-axis, it's going to be the area mapping up from the function to the x-axis, and when the function is above the x-axis, we'll map down to the x-axis, and we'll have a negative integral here, positive integral here. However, this function lives above the x-axis more than it does below on this interval. Therefore, we should have a positive integral, which we do. All right, so for our next example here, let's look at the definite integral from 1 to 2 of x squared plus 4 all over x dx. And similarly here, we're going to need to split this up. So this will be the definite integral from 1 to 2 of x squared over x plus 4 over x dx. So this will be the definite integral from 1 to 2 of x plus 4 over x. Now the thing to remember here, that when we integrate this, of course the integral of x will just be 1/2 x squared. No problems there. It's this 4 over x. Don't use your power rule there. That is a natural log. Right? That's going to be 4 times the natural log, the absolute value of x. Now, in this case, since we're evaluating from 1 to 2, we can actually drop the absolute value bars if we want, because we're only looking at positive x's, so we don't really need to worry about it here. Of course, it doesn't hurt to, put it always just to be sure, right? Okay, so, we're pretty much there now. We're going to plug in our 2, so get 1/2 times 2 squared plus 4 ln 2. I'm definitely going to drop the absolute value bars there. And then we'll plug in 1. So it'll be 1/2 1 squared minus 4 natural log of 1. Now, nice thing here is natural log of 1 is 0, right? So this is going to be 1/2 times 4, so that'll be 2, plus 4 natural log of 2, minus 1/2. Okay, so this is 4/2, so we're going to end up with 3/2 plus 4 ln 2, and there we go. That we can just leave our answer like that. Now what you might see in the book that they bring this up as 2 to the 4th to give you 16, right? They might say this is 3/2 plus natural log of 16. Don't get all weirded out if that happens, okay? That they're just moving that 4 up. I don't find that necessary, but that you may see that if you're checking your answer in the back of the book. All right, and looking at the graph here, here's what the graph of this function looks like, and here's that area from 1 to 2, and it ends up being this 3/2 for ln 2. If you plug that in the calculator, you get about 4.273. Okay, and if you think about this, if you think about it, this is a rectangle here with base 1, height 4 right here. So that would be 4, and then we have point other stuff there. So that does actually line up with what this should be. It should be about 4 point something, and that's what it is. It's about 4.273. All right, up next, let's look at the definite integral from 0 to pi over 4 of secant squared x dx. Okay, so you know, you're not getting away from trig, right? You thought you might have avoided it here, but no. But remember, secant squared, the integral of secant squared is just tangent. So this is a tangent of x. We're going to evaluate it from 0 to pi over 4. And so the fundamental theorem of calculus, where we're plugging this in, we'll have tangent of pi over 4 minus tangent of 0. Now, tangent of 0 is 0. Tangent of pi over 4 is 1. So we get 1 minus 0. So we get an area of 1. All right, a lot nicer here than what it looked like originally. All right, and so just to take a look at the graph, here's the graph of secant squared. And then here's the definite integral from 1 to pi over 4. And the area of this shape here ends up being about 1. Okay, so this problem is going to be a little more abstract, but let's consider the right triangle with height h and base b, and we want to use integration to verify the area of this triangle. So we know that the area of a triangle is 1/2 base times height, right? But will integration verify this? So let's say that we have a triangle, any triangle, and we're going to put it here, okay, so that we have, we'll say our base is b and our height is h. Okay, so we're going to put it on the xy plane in this way, okay, so where the right angle is at the origin. Okay, so what we want now is, well, one, I want a function that can give us this line that we've made. We're going to use integration to find this area. Okay, so this line, well, it's going to be a linear function, right? And its y-intercept is h, right? So that's the y-intercept. And it's going to have a negative slope, and its rise over run, okay, is, well, h over b. Right? Now, there are a lot of ways that we could find this, a lot more ways we could find this, but that's one way. So another way is using like the point slope form and all that. Okay. Now, The area, well, I'm going to set up an integral from 0 to b. All right, so it'll be 0 to b of this function, h minus h over b times x dx. Okay, so h is a constant, right? So when we integrate it, it'll be h times x, then minus h over b times 1/2 x squared, okay, from 0 to b. All right, so now we will plug in b, so we'll get h times b minus h over b times 1/2 times b squared. All right, so that's plugging in the b, then we're going to plug in the 0. Well, these two things go to 0. So it'll be 0 minus 0. And so we're going to get h times b minus h over b times 1/2 b squared. So here, this b cancels with one of these, so we have hb minus 1/2 hb, which ends up being 1/2 hb, or 1/2 base times height, which does line up with what we know about the area of a triangle. Okay, so like I said, this one was a little abstract, but just to show you that there are a lot of things out there that you can use integration for to find the area of formulas. In Calculus 2, for example, once you have more techniques, you can do this to find the area of a circle, or of an ellipse, or many, many different things. Okay? All right, what about u substitution? Can we do u substitution with definite integrals? And the answer is yes. However, when you make your substitution, right, when you have a to b f of x dx, when you translate that into an integral in terms of u, I guess it would still be, now let me just call this, g of u du. You have to change the limits of integration as well, because these are going to be x's. You need now u's. Okay, so you need u going from, let's say, c to d. Okay, so the answer is yes, we can do u substitution with definite integrals, but you have to also translate the limits. These are called the limits of integration. But if you do that, you don't have to translate back to x's. You can leave it in terms of u. Right, so that is a bit more work on the front end here, but less work on the back end. You don't have to put the x's back in. All right, so to give you an example, let's look at the definite integral from 0 to 2 of 2x all over x squared plus 1 all squared. So this will definitely be a u substitution since we have stuff squared in the denominator here. Right, so this is going to be our u. So we're going to let u be x squared plus 1. So then du will be 2x dx. And we have that exactly here, 2x dx. So this we could just translate straight to du, or you could do your divide by 2x on both sides and cancel. But since I see that exactly, I'm just going to translate it over. Okay, now, when we move over, keep in mind that these are x's. X goes from 0 to x going to 2. However, when we translate into u's, okay, in the denominator we will have u squared. In the numerator, I'll leave the 1 and put du out here. You could put it up top. Doesn't matter that much where you put that du, as long as you don't put it over here. Right? It does need to either be on the top of the fraction or off to the side. Now, when we make this transformation, we need new limits. We need u limits, because these are x limits. These aren't going to be the same as our u limits. So here's how you do it. You take these x values and plug them into your u. Okay, so you take 0 plug it into u, and you take 2 and plug it into u. Okay, so for example, I write it like this. U of 0 is going to be 0 squared plus 1, which is 1. So our lower limit is going to become u equals 1. Then we're going to plug in 2. So u of 2 is going to be 2 squared plus 1, or 5. Okay, so our upper limit is going to be 5. So our new integral is the integral from 1 to 5 of 1 over u squared du, or a simpler way would be, maybe not simpler, but a power rule way would be u to the negative 2 du. Okay, and so now we are able to integrate. All right, so we'll have u to the negative 1 all over negative 1, okay, evaluated from 1 to 5. So I'm going to rewrite this a little bit so that it's negative 1 over u from 1 to 5. All right, so that is going to be negative 1/5 minus a negative 1 over 1. Okay, so let me put them both in parentheses here. All right, so I have negative 1/5 plus 1, that's 5/5, so the whole thing comes out to be 4/5. All right, so if we wanted to look at the graph, so here's our original function, right? F of x equals 2x all over x squared plus 1 all squared, and that original integral was 0 to 2, and you see here we got 0.8, 0, 0, 0, 0, 0, so that is, if you, right, 4/5 is 0.8. Notice that we get a bunch of noise here, and that's because software can only really approximate. It doesn't do a super great job. But here's the original area that we were looking at. Now, if we graph the u function, so this is what 1 over u squared would look like if this was the u-axis, okay? And we instead were looking at the integral from 1 to 5, so this area. Now, if we look at what the software gives us, you'll see it's 0.7999999. Once again, it's still 0.8, it's just there's errors in the approximation. What's happening is when we make this transformation, we need to basically change the limits of integration, because if we don't, well, here, if we tried to plug 0 into the function with u, we get a bunch of garbage, right? We'll get blow up, division by 0, okay? So what we're doing is translating this area into another area, but they end up being the same, okay? So that's essentially what we're doing when we do u substitution with a definite integral. All right, to give another example involving u substitution, let's say we have the definite integral from 0 to 2, x cubed times the square root of 16 minus x to the 4th. So of course, we have the square root of stuff, so our likely candidate for u is going to be what's underneath the square root. So we let u be 16 minus x to the 4th, then du is going to be negative 4x cubed dx. All right, and so this one I'll go ahead and do the division, du over negative 4x cubed. I'll bring the negative outside. That's equal to dx. All right, and so now we will just do our direct transformation here. So I'll have x cubed times the square root of u. Okay, then times negative du over 4x cubed. And the x cubeds here cancel, which is exactly what we want. However, another thing that we want is to move these x limits to be u limits. Okay, so in order to do that, again, we just plug in our x values. So u of 0 will be 16 minus 0 to the 4th, which will be 16. So the lower limit is 16, while the upper limit, well, we'll plug in the 2. So it'll be u of 2. It's going to be 16 minus 2 to the 4th. Well, 2 to the 4th is 16. So the 16 minus 16, which is 0. So we get 0 as our upper limit. Now, this might seem a little strange, right? So if I move this negative 1/4 to the outside, what we have here is negative 1/4 times the integral of 16 to 0 of the square root of u du. And this is where that rule we talked about last time comes in, where we can flip the order of integration and negate it. So if we want to flip this to be more like what we like, 0 to 16 instead of 16 to 0, we can, we just negate it. And since it's already negative, we can just renegate it. So we could have negative times negative 0 to 16. I'm going to write this as u to the 1/2 du. Or 1/4 times the integral of 0 to 16 u to the 1/2 du. Okay? Now, I will tell you, you don't have to do this. If you just go ahead and do this like you normally would, plug in the 0, subtract by plugging in the 16, you will get the same answer. This just looks cleaner. Okay? So now, we integrate. So that 1/4 will just come along for the ride. The integral of u to the 1/2 will be u to the 3/2 times 2/3. And that 2 will cancel with the 4 and leave a 2. And we're evaluating this from 0 to 16. Okay, so we're going to have 1/6 u to the 3/2 from 0 to 16. Now, we can do what we did before, where instead of u to the 3/2, we write this as the square root of u cubed. And we would do that because we know what the square root of 16 is. Right, so we'll get 1/6 times the square root of 16 cubed, right? Then minus 1/6 square root of 0 cubed. So this piece just comes out to be 0. Always like it when 0 is our lower limit. Okay, so this will be 1/6 times the square root of 4. Whoops, sorry, not square root, but 4 cubed. Right, which will be 64 over 6, which simplifies to be 32 over 2. And there we go. Okay, now one thing to keep in mind is when we don't translate it back into x's, notice that what we're plugging into is a lot simpler than if we were plugging x's into this. If we were plugging x's into the 16 minus x to the 4th stuff, that's a lot more complicated than just plugging in 16 into this thing. Okay, so it may seem like an unnecessary step, but it actually does make our life a lot simpler, at least in that respect. Okay. All right, so next up, let's look at the definite integral from 0 to pi over 4 of tangent of x dx. So we don't have a rule for tangent of x. However, we do have u substitution, right? Because tangent is sine of x over cosine of x. And now we can let u be the denominator of this fraction. So when we do that, if u is cosine of x, then du is negative sine of x dx. Okay, and if we do our division idea, where du over negative sine of x is dx, we can do our direct substitution there. Okay, so we will get, I'm going to leave the limits alone for a moment. We'll have sine of x over u okay, times du over negative sine of x. Okay, so the signs cancel, which is exactly what we want. Now, again, we have x limits here. Okay, so we want to put in u limits here. Right, so let's do that. Again, we just plug in the value. So we're going to plug in 0. So u of 0 is cosine of 0, which is 1. And u of pi over 4 is going to be cosine of pi over 4, which is square root of 2 over 2. Okay, so the lower limit becomes 1, and the upper limit becomes root 2 over 2. Right, so when it's all said and done, we have the definite integral from 1 to root 2 over 2 of negative 1 over u du. Now, we can again flip the limits of integration here to get, instead of a negative, a root 2 over 2 to 1 of 1 over u du. Okay, now this is in a much better order, mainly because we're going lower number to higher number. Okay, so now we're ready to integrate and use the fundamental theorem of calculus. So the integral of 1 over u is the natural log absolute value of u, which again, we could actually drop the absolute value bars here because we're only dealing with positive u's. But again, as I said before, it's good to kind of have that practice. All right, then we'll plug in 1. So I have the natural log of 1 minus the natural log of square root of 2 over 2. Okay, and natural log of 1 is 0, so we end up with the negative natural log of root 2 over 2. Now, some of you may feel a little weird about this because, hang on, shouldn't this be positive, right? If you look at the area beneath tangent from 0 to pi over 4, it's above the x-axis, right? So here's the graph. It's above the x-axis. We should get a positive value, but keep in mind the weird way that natural log works. For values less than 1, ln itself is going to be negative. Okay, so one thing we can do, actually there's a lot of things we can do. You can actually move the negative to the inside. You can split this up. If we were to split this up, we'd have natural log, well, actually, it'd be 1/2 ln 2 minus ln 2, right? Because you can split up the division with subtraction and move the 1/2 power outside. Then if we distribute the negative, we'll have negative 1/2 ln 2 plus ln 2. So we have a full ln 2 and we're subtracting 1/2 of ln 2. So this comes out to be just 1/2 natural log of 2. And if we wanted to bring this all the way back in and say that this is the natural log of square root 2, we could. And there we go, a nice positive value for our area. Okay. Again, this is not actually necessary. This is just in case you want to simplify it all the way down. I consider this a perfectly fine answer. All right, so for the time we have left, let me briefly discuss what's considered part 1 of the fundamental theorem of calculus. And you'll see why we didn't really mess with it very much. It's sort of the other direction, right, of instead of going from definite integral to antiderivative, this is sort of taking the derivative of the integral. And it shouldn't be that surprising what this is saying. So basically, what the first part of the fundamental theorem of calculus says that if f of x is continuous on a to b, then the function, the definite integral, so this is sort of a weird function we have here. It's the function that is the definite integral from a to x of f of t dt. Okay, this is continuous on the interval a to b and differentiable on the open interval a to b. And it satisfies this property, that if we take the derivative with respect to x, okay, of this function, definite integral from a to x of f of t dt, is going to equal f of x. And the reason this is if you think of the second half of the fundamental theorem of calculus, if you are trying to take the derivative of this function, right, the definite integral from a to x of f of t dt, by part 2 of the fundamental theorem of calculus, the one that we've really been dealing with, this is going to be the derivative with respect to x of, well, again, by the fundamental theorem of calculus, it will be capital F of x minus capital F of a, and this is where capital F is an antiderivative of little f. Okay? And so when we do that, now we're taking the derivative with respect to x of capital F of x minus capital F of a. So the derivative of capital F of x is going to be capital F prime of x, right? And then the derivative of capital F of a, well, this is just a constant, right? This is just going to go to 0 when we take the derivative. So this whole thing ends up being capital F prime of x, but since capital F is an antiderivative of little f, that means capital F prime is little f of x. Okay, so that's basically what this is saying. It's a long-winded way to basically say, hey, if you differentiate an integral, you're going to get back to the original function. Okay, so in other words, this is a way of saying that the derivative of an integral of little f, right, these cancel and we end up with little f. Same thing as if we integrate f prime, we're going to end up with f, possibly with a plus c. Okay, that's sort of the difference there. So that's just, you know, another way of sort of talking about the fundamental theorem of calculus. This is something that you're more likely to see pop up in, if you go on to take differential equations or something like that. As I said in this class, the more applicable version of the fundamental theorem of calculus that's actually usable is part 2. Part 1, I think part 1's neat to kind of look at, but as far as it being super useful now, maybe not so much. Super useful later on, yes. Say calculus 2, differential equations, this will pop up. But you will, you'll actually get a better explanation of how it pops up and how to use it when that happens. Okay, so as far as this lesson, I want to at least introduce it and show it. But as far as being successful in Calculus 1, it's the second part that is really paramount. All right, so I think that is good enough for right now, and I will catch you all in the next video. Cheers!